Welcome to Introduction to Quantum Field Theory, episode 30, and this one will be talking about scalar fields with a Yukawa interaction. We'll get right into it. From the last video, or the second to last video, no, it was the last video, from the last video, okay, instead of just writing all that sentence, I'll just write down the Lagrangian. We were considering the total Lagrangian, which was the Lagrangian of a scalar field plus the Lagrangian of a spinor field plus a coupling G to a Yukawa interaction. This is what we introduced in the last video. And in this video, specifically, we will focus on this right here. So in this video, we will focus on using a Lagrangian, which is just going to be the scalar Lagrangian, and the Yukawa interaction. So as this is, or not as this is, I didn't expand this into its full form, which I have in my notes. It's the gradient of the field squared, then minus the mass of the field squared. And then now we get this new term where this G, let's this over like so. This G, which shows up here and here, this is the coupling strength. Cannot spell for some reason. The coupling strength. And then this right here is the conjugate spinor. Conjugate spinor. And the conjugate spinor, recall, is the Hermitian conjugate and then gamma naught. So now we're going to look at the inhomogeneous Klein-Gordon equation. So because this results in the inhomogeneous Klein-Gordon equation, which is partial mu plus m squared. Okay, I made a mistake in my notes. Oh, I accidentally erased it in my notes because if I erase on one side of the paper, it can erase the stuff on the other side of the paper. So when I was erasing something on the opposite side of the paper, it erased the squared. And then it's equal not to 0, but to the derivative of an interaction term with respect to the field. We have this. And now we can see that the interaction potential is as follows. It is V equal to the coupling to the Yukawa interaction, which is just G C bar C phi. So therefore, the inhomogeneous Klein-Gordon equation becomes the following. We get partial mu plus m squared b equal to g c bar c, because it's a gradient or the derivative with respect to phi, and you just have one phi here, so it cancels out, and you just end up with this. So now we can do as we've been doing with other interaction types. We can rewrite the solution. Then the solution is phi of x mu is the integral over y. Then this interaction, which is dependent on the field, which is dependent on y, and then times the special solution. Like this. So this is the solution, and now expanding it, we end up with g and the integral over y of c c b s. So now this is pretty tough to solve in general. This is a a really difficult equation to solve. So what people like to do is the same thing we did in the last video where we made a perturbation ansatz right here. So we're going to do another one of those things. So we get perturbation to perturb the system. And namely, if g is less than 1, then we get c is equal to phi naught plus g phi naught plus c squared phi naught, sorry, phi 1, phi 2, and so forth. And we get c is equal to c naught plus g c1 plus g squared c2, and this goes on. And this implies that it also exists for the c bar, for the conjugate spinning. So this is the perturbation ansatz. So what we're going to do is then plug these into this solution right here. And then we're going to equate terms of g just like we did before with terms of lambda. So therefore, we have phi, the field is going to be equal to g times the integral over d to the 4y c bar c ps. And then I'm going to stop writing the x y thing here just because it's a lot to write. I'm just going to put phi s. So we get this, which is equal to g integral this, and we get c bar naught plus g c bar 1. And I'm only going to include two terms because that's just You don't need more than that to show how this works. And then otherwise the multiplications start getting pretty complicated. Okay, so this, and now we can expand this out again. Integral, get C, C naught. So these are the terms that have no G. So the term with no G is this. Now we're going to do the terms with 1G. So plus 1G. Well, this is the only one with 1G, so we get G times C1 bar, this, and then this times this. So we end up with C naught bar, C1 plus C naught, C1 bar. And then we're going to have G squared. The only term that will give G squared is this times this. So we end up with G squared, C1 bar, C1. And then it keeps going, ds. And now we're going to move this G to the inside here. So this ends up being a factor of G. This ends up being G squared. This ends up being G cubed. So there's that. So now equating factors of G, we can see that the solutions are phi1 integral over y of C naught bar C naught phi s. And likewise, phi2 is equal to integral over y of C naught C1 bar plus C bar naught C1. I'll write it in the same way that I had it before, like this. Cs. So we get this. And then, so I'll just write the third one. Integral over y of C bar 1 C1 ds. And this just continues on and on. Now we'll draw a picture for this term, but for drawing these terms, we're going to need to wait till one or two videos from now, because we need to cover direct equation Green's functions before we can fully interpret these. But I'll draw the picture for this one. And that is for phi1, the picture is have that. You have your position, your x and your y. So x mu, y mu, and this is your connection type, not connection, but the special thing that's relating position y to position x. And these are, in a sense, reaching out and interacting with C naught and C naught bar. So you have at point Y, the spinner and the conjugate spinner interacting at this point, and then this is then related to the point X. So that's what's happening there.